Okay, it's about time, so um, let's continue. Again, if you have questions regarding the homework and the writing projects and anything, just send me an email before the class starts so I can get the right solution so I can present in class. Okay, we were talking about homogeneous case and the linearity principle. I talked with you guys, several of you guys, and I received several questions regarding how to understand this. So I think we need to go deeper in that. So number one, this is the homogeneous case. All right. What's so special about it? Well, you can think about this. If y is a solution, that basically means y satisfies this. Then a constant times y, okay, if you take the prime, is going to be a constant times c prime, y prime, which is going to be c times at y, using this fact, which is cy. Okay. This implies that if y is a solution, so is a constant times y. cy is also a solution. Okay. Similarly, if y1 and y2 are two solutions, then we know y1 prime equals aty1, y2 prime equals aty2. Therefore, y1 plus y2 is a new function, and this function satisfies which equals aty1 because y1 satisfies the first equation, and aty2 because y2 also satisfies the equation. And you can factor out at and give them y1 plus y2. So something prime equals at times something itself. This implies so is y1 plus y2 or y1 minus y2. Okay, that's what we can get from the homogeneous case. Then, what's the implication? The implication is if you have y1 as a solution and y2 as a solution, okay, then so is any linear combination of y1 and y2. In physics, this is called superposition of solutions. Okay. So have you guys heard about superposition of waves and things like that before? Like you have one wave, you have two waves, you put them together, that's going to be a third wave. Okay, and the third wave satisfies a certain kind of principle. So that's basically telling you this. If you have a wave going to the right, if you have a wave going to the left, both are solutions, okay, of something called a wave function. Oh, sorry, wave equation. Then what it says is when you put these two waves together, when they meet each other, you're going to have something which is a superposition of these two waves, which is basically these two waves adding together. You have something like this when they meet. Okay? Basically, it tells you this is also a solution of the wave equation. And even after they meet each other, this keeps separated again. Okay, so going from here to here, when they combine together, and then they leave each other. Okay, that's basically how you solve the wave equation. It's just like you have several waves, 3 waves, 4 waves, you add them all together, it's still a wave, and that wave still satisfies the equation. That is called superpositioning. Okay. So this is true because You are trying to solve the linear homogeneous wave equation. That means when you are trying to solve non-homogeneous wave equation, the superpositioning is not true. Okay, you add two waves together, it's not a solution anymore. That also means if you have a nonlinear wave equation, you cannot simply add the two waves together and become a third solution. Okay, so these two are necessary, linear and homogeneous. So that's kind of like understanding the same thing from a physics perspective, and probably the most straightforward case is the superpositioning of waves. All thanks to that, wave equations is linear. If it's not linear, this is not going to happen. Okay. By the way, do you guys know any waves which are nonlinear? Which means you cannot do the superpositioning. Okay, that's the gravitational wave. That's why it's hard. This wave is highly nonlinear. This wave even interferes with itself as it propagates. This one is coming from the general relativity equation. And the key is general relativity equation is nonlinear, fundamentally nonlinear. That's why all the traditional concepts about waves fail. Maxwell's equation is linear. So any wave you get from there is going to be linear. You can do superpositioning. Okay, so that's some examples to help you to understand this thing from physics. Superpositioning, that's probably the term you're more familiar with. But basically tells you, this one tells you this. Y prime equals this, which is homogeneous case. And basically the solution can be represented as the linear combination of only a few solutions. Because we want to ask, like, please find all the possible solutions. You just say, hey, there are infinite many, but fundamentally, they're just all the possible linear combinations of a few. Because if y1 and y2 is a solution, so is their linear combinations. Okay? We won't go too deep, but this is certainly related to basis and the subspace in linear algebra. There is a lot of work there. Okay? And the way to find the solution is find a basis, and then all the other solution will just be all possible linear combinations, which is the subspace. All right, now for non-homogeneous. We can actually write them down. Let's say we have two solutions. This time it's non-homogeneous, so we have a BT. Okay. Now what about y1 plus y2? Well, it's going to be y1 prime plus y2 prime, which is h prime aty1 plus bt plus aty2 plus bt, which is aty1 plus y2 plus 2bt. This implies y1 plus y2 is not a solution, even though both are. Okay. For y1 plus y2, you need a 2 here in order for that thing to satisfy. So this is not going to work. That's why for non-homogeneous, you cannot simply find several solutions and do all the possible linear combinations, because the linear combinations won't be a solution anymore. Okay. Now what you want to do is you want to simply take the minus, and you find a very interesting fact. That is, if I take the minus, this is going to be AT y1 plus BT minus AT y2 plus a BT, which is AT y1 minus y2 prime, y2, not prime, plus these two always cancel each other, no matter what BT you put in. This implies y1 and y minus y2 satisfies okay, and now if you take a look, this is the homogeneous case. Okay, that's the fact we wrote down. That is y1 equals y2 plus yh, where this yh is the one which satisfies the homogeneous case. That's where the linearity principle comes from. Okay. All right. So now to write everything down, it's clear now. This is linear, but not homogeneous. What you want to do is you want to first solve the homogeneous. Your solution should be a linear combination of a few solutions. That works for homogeneous case. And then every other solution of this for the non-homogeneous case will just be whatever you find here plus a special case. Because this minus that will always be in YH. Okay, so this is a special case, one special case. That's how we solve the general linear equation or system or transformation, whatever. Okay, it always works. Okay, so that's the relation between the homogeneous and the non-homogeneous. This one contains the most of the information. This one contains just a little bit more additional information. Putting these two information together, you have the general information. Now from physics, again. We have a relation between these two. Not always true, but very commonly true. The homogeneous case usually corresponds to a free system, like a free particle, a free wave, which basically means no external force, no external energy, no external anything. Okay. And the non-homogeneous case is basically the homogeneous case plus an external source. That's the relation between them. For example, you can have a free electron that satisfies a certain kind of motion equations, which is homogeneous. Okay, that's in moving a certain way. Now, what you can do is you can have an electron, but this time it's not free. You say in an electronic field. Then the whole thing becomes non-homogeneous. Okay, and the only part which is in addition is just this external electric field. Sometimes it's external force. Sometimes it's external potential or energy. Okay, and by the principle, it basically tells you it's almost equivalent to solve the free one, and then add a little bit thing, a little bit more term there. You will have all the possible solutions now. That's why in physics and differential equation, a lot of energy has been focused on this. Because if you add something external, it's just taking this one and add a small disturbance, and that's it. All right. Hopefully this helped you to understand a little bit from all perspective, how to understand homogeneous case and non-homogeneous case. Okay. One point of view is from linear algebra, and the second one is from physics. Any questions before we move on? All right, now let's move on to 1.9. We are going to go ahead and try to solve all the linear equations. We call it integrating factor for linear equations. We focus on y prime equals at y plus b. All right. Example. Y prime equals negative 2 over ty plus t minus 1. This is linear. This is your AT. This is your BT. All right. To solve it, the first thing I want to do is I want to move all the y prime and the y to one side. Leave everything with BT on the other side. That's good. Now next, I want to take the integral on the right-hand side, which give me t squared minus t. Great. I also want to take the integral of the left-hand side together. From here, you can see you're not be able to do it because this is not the derivative of anything. Still okay? So the key is, can we do something to make this one look like the derivative of something? If that's the case, take the integral, the thing inside will be our answer. Still okay here? Okay. Now question, have you seen anything like this before? You take the derivative, you have y prime and y, and with a plus. Have you seen anything like that before? That is y times something else. And then we have y prime mu plus y mu prime. That's called a product rule. Make sense so far? Okay, so you wish this one look exactly as this form. Still okay? You wish what you have here is a mu, and what you have here is just a mu prime. Then everything is perfect. Still okay? But here's the problem. You must be really lucky because you need both of them to be nice at the same time, and they're related. In general, these two can be anything. They don't have to be related. Still okay? So our key part here is, and think about this, we're going to times a factor here to change this one and this one at the same time. But after we change it, it becomes perfect. This one become exactly the derivative of this part. Then everything will be perfect. We have the product rule, we can do the integration, and so on and so on and so on. Sounds good? Okay, so this is what we're going to do. I'm going to time this one by something. I don't know what that thing is. I just timed it by mu prime. Plus this. And of course, I times up this mu, okay, on t minus 1. This is still true. I don't know what mu is. Okay. But after I finish that, there's one thing I wish to be true. That is, this one give me exactly the product rule. So I can take the integration. Something here. Still okay? We can call it V or whatever. And what we're hoping is this one is exactly V prime, and this one is exactly V. Or in another word, we really wish the derivative of u times 2 over t prime equals mu. Times, hold on, what do I want? I want, hold on, what am I trying to do here? I times this one, I want this part to be the derivative of this part. Hold on, what am I trying to do here? It looks right. I want this part to be the derivative. I want that part to be the thing. So what I want is the reverse order. Okay. Hold on. I want mu prime equals mu 2 over t, because I want this part to be the derivative and this part to be the original thing. Okay. I want a mu satisfying this. Then take a look. What is this? It's a homogeneous linear equation which we can solve. It's separable. So mu prime over mu equals 2 over t. Take the integration. Ln mu, let's just use this. Okay, equals 2 ln t plus a c. We just need some mu, so any c will work. Let's just take c to be 0. Let's finish it and then take c to be 0. Then mu equals e to the 2 ln t, which equals e to the ln t square, which equals t square. If mu is t squared, now go back to what we have here. The first thing I want to do is times t squared on both sides. T squared y prime plus 2t y equals t cubed minus t squared. Take a look. This become t squared y prime. Where if you take the derivative, first you do y prime, keep t squared. Second, you keep y and do the t squared, which give you 2t. So they matched. And now if you take the integral, this gives you t squared y equal 1/4 t fourth minus 1/3 t cubed. Your y is going to be 1/4 t squared minus 1/3 t plus a c. All right. There is a lot of work here just to complete the problem. But focus on the key part. What did we do exactly? Basically, what we did is we timed a mu on both sides. And suddenly after we do that, the whole thing becomes solvable. Okay. Then our job is try to find the correct mu. Once we find that, we multiply it, the whole thing becomes solvable. Sounds good? This mu is called the integrating factor. Okay, so that's how we do this example. I think you can follow all of the details, but now let's write it down in a general notation for general case. Okay. Integrating factor. Let's summarize our idea. Did an example. Number one, we start with this. Okay. First job, we change it to be this. Okay. We move y to the other side. To be consistent with the book, we rewrite this one into plus gt. Just with a plus equals bt, where gt equals negative 80. That's step one. Rewrite everything into this format. Step two. What we want to do is we want to times a mu y prime plus a mu, let's write it more clearly, mu t gt y equals mu t bt. This mu t is called integrating factor. What's your hope? Your hope is after you do this, the whole thing on the left become a product rule. For some, let's just call Vt. Actually, let's just call it mu t. But now ask yourself, if you do the product rule of this, what do you need? You need mu y prime, which is here, great, plus mu prime y. Still okay here? To make this happen, this whole thing here has to be mu prime. Otherwise, I don't have this nice format. Still okay? This provides you a hint how to find the mu. You need to find a mu such that this part gives you exactly mu prime. And once you have that, this can be done. Okay. Still good so far? All right. So how do you find mu? Technically, what you should do is you should go ahead and solve this. Why? Because this is a homogeneous linear equation. Moreover, this is actually separable. It's always separable. Okay. Finally, once you finish this, the rest is just try to finish the thing. And you just take the integration. I think it's pretty easy. Okay. This may be hard, may be easy, don't care. And finish. And solve. All right. Go over all the steps here. Make sure you understand the core of this thing. We were looking for a factor to multiply on all the side. In order to achieve that, the left-hand side become a perfect product rule. To get the perfect product rule, we need to have mu and mu prime in these two terms because we already have y and y prime. Okay. Then we need to pick a special mu such that this part is exactly mu prime. That will require us to solve an equation. And that mu will do the job. Still okay? Once you have that, whole thing can be continued. All right, let's try an example. Let's follow it slowly. Let's take y prime equal negative y over 1 plus t squared. Step 1, move it. Step 2, times a mu t, such that it satisfies mu prime equals mu times 1 over 1 plus t. Okay, if you think this is confusing, just rewrite this one to be mu y prime plus mu times 1 over 1 plus t. Y equals mu times t squared. And you're hoping this is mu prime. I think that's clear. You're looking for a product rule. Therefore, mu prime has to be. This is always separable, so it's always doable. Okay, this tells you ln mu equal ln 1 plus t plus a c. Any c will work. Let's just, for simplicity, take c equal to 0. The mu equals 1 plus t. Integrating factor. Sounds good? Now multiply this into the original thing. Now, but this time you know what mu is. So plus 1 plus t times 1 over 1 plus t y equals 1 plus t times t squared. This time you have 1 plus t times y, the whole thing prime, If you don't believe in so, you can quickly check. This equals 1 plus t times y prime, which is exactly the first term, plus 1 plus t prime times y. And you can see it's exactly the second term. The left become a perfect product rule. And no surprise, because you made it so. You made it so. Of course it will work. Finally, if you take the integration, so finally y equal cube plus 1/4 t4 plus a c divided by 1 plus t. All right. That's all we have for integrating factor. It's a very easy idea. In class, I hope you get the idea. Of course, you're not familiar with that now, but after 3 or 4 homeworks, I think you would totally see how this thing works. Okay? The key is find the integrating factor by solving this. Second, multiply the integrating factor on the other side. You are definitely going to have a perfect product rule. If not, go back and check. You set the wrong thing up. Okay? Once you have that, it's doable. Some good news. First one is, this one is in general pretty easy to solve because it's always separable. It's always mu times a function. So it's always separable. Second good news is, notice that if you multiply mu on both sides, this is okay because the left-hand side become a perfect product rule. The right-hand side is also okay because no matter what, it's just going to be a something with t and something with t. So when you finish, it's still a function about t, so you can take the integration with respect to t in no problem. What you are afraid of is actually if you multiply by a y, something related to the y, then that changes the whole thing. The good news is integrating factor has nothing to do with y, but only t. Okay? So that's the good news. From here, I think everything is clear for integrating factor. Any questions so far? All right. More practice, I would say you will see this is easy. It kind of looks cheap, right? You're trying to do something and you somehow you just guess the format and suddenly nothing just worked. If you think this is cheap, this is not solid, this is like, yeah, you're lucky, get used to it. Because most of the cases for solving differential equation, we're just guessing. And nicely for some kind of format, the guess always work. Okay, in general, it's difficult. It's really difficult. Okay. All right, that's everything with this. And that's everything with chapter 1. Let's move to chapter 2. This time, we're going to do first order systems. Well, why do you need that? Let's talk about modeling. Yeah, systems. We talk about this. That's like exponential growth, and then we have logistic growth, and such and such and such. Okay, this is great before, but now we simply want to extend it to, what if you have 2 species? Then you should have 2 equations, 1 for each species. Okay. Then the first classic example is going to be predator and prey model. We have 2 species, the predator. In our case, we call it the fox, and we have the prey, which is the rabbit. Okay, we call it F, we call it R. Now let's check the first easiest model. If there's no fox, only rabbit, what's going to happen is dr over dt equals alpha r, which is just exponential growth. That's for rabbit. If there's no rabbit, only fox, then fox die out. So you have exponential decay with a negative rate. Why? Because you don't have food. There's no rabbit, the fox eventually dies out. Stay okay? Now, of course, they interact with each other. If you have rabbits, you have exponential growth, but if you have a fox presenting, that thing should be negatively related to the growth rate. Due to rabbits are captured by the fox. And of course, the fox is not going to die out, hopefully, because now they have supplies of food. Okay. Food. From here, clearly you see a system because you have two species and they are interconnected with each other. Okay. The population of one affects the other. Okay. Several things. R stands for rabbits. Population. F stands for fox population. Okay. Alpha is the growth rate of rabbit. Your gamma is going to be death rate or decay rate of fox. Okay. Beta and the delta will be the interacting coefficients. You have done some modeling yourself, so you know this term is not perfect. It just captures some essential properties of the interconnection, but of course it's not perfect. Okay. Can I explain why it's related to R times F for both of these? That means the more fox, the easier for the fox to capture the rabbit, or like the fox capture more rabbits. Okay. Also means the more rabbits, it's easier for the fox to capture the rabbit, even if you keep the fox population to be fixed. Still okay? That's why we have R times F. No matter which one is bigger, it's always easier for them to capture each other. Second, why aren't these two terms different, the same? Because clearly this is how much rabbit dies by captured by the fox, and this is how much the fox consumes, right, by capturing the rabbit. These two terms should be the same. Now just keep in mind, even if a fox captured 10 rabbits, it doesn't mean that you're going to increase the fox by 10. Then you have a hidden assumption that is one rabbit can feed one fox. Sometimes the ratio can be 5-1 or 10-1, depends on how much food they need. That's why these two constants, even though they're very close to each other, both R times F, but they should have a different constant here and here, simply because the ratio is not 1-1. Okay, it may be 3-1 or maybe 5-1. Sounds good? Predator, prey. We have a system of equations. Usually we put a big bracket to indicate they are connected. Okay. Number 2, how do we analyze it? Well, how do you analyze a first order equation, which is not a system? Number 1, we can solve it. We know this is hard and next to impossible in general. Okay. What else do we have? We can do the slope field. Just get roughly the idea of this thing. How do we do the slope field again? That means given any x and y, actually t and y, I can give this, and things like that. So I know the derivative. I can do things like that. Still okay? Now similarly, check this thing. If I know R and F, I can also produce the derivative, but that's going to be the derivative of R and the derivative of F. So what we have is this. This time not t and y. Instead, we have one species and the other species, rabbit and fox. Every point here is going to be R and F. Still okay? And then what are the changing rate do I know here? I do know dr over dt and df over dt here. That's the two things I can compute from the system. What if this is 3 and this is 4? That means I can put a 3, 4 here. What does this vector represent? It represents for this moment, both the rabbit and the fox is going to increase, and they increase at a different rate. One is 3, one is 4. Still okay here? Okay, from this you can see it actually makes sense to put a vector here. This vector should be dr over dt and df over dt. This one basically tells you how the population is going to change, but just keep in mind, this is not t. This is one species and the other. We don't call this slope field anymore. We call it the phase portrait, which corresponding to the phase line. All right. Number 3, we also can do equilibrium in in equations. Can we also do equilibriums for system? Okay. Well, to find the equilibrium, you should basically set this one to be 0. Okay. Meanwhile, you want this to be autonomous. Okay. After that, you know the long-term behavior. You know equilibrium. You know it's a sink or source, which means it's stable or not stable. Now what you have is dr over dt, df over dt equals something. Okay. Can you do the same thing? Number 1, define something which is called autonomous, which has only something to do with r and f, but not t. Okay. And then go ahead and try to solve this equal to 0 and this equal to 0. That means what? That means if your rabbit and your fox population is right at here such that these two is true, then they won't change at all because the derivative becomes 0, both for r and f. Still okay? That means your population stay there, which make it equilibrium. Moreover, we can also talk about this is stable or a sink, or unstable, which is a source. And now you can imagine it may be stable in terms of rabbit, but not stable with fox, because you have 2 species now, right? So 2 nodes can have different type. We will handle that later. But certainly we can talk about it. Of course, number 4, we can solve it numerically. This is the beauty. The way to solve this is exactly the same as before. Because for computer, They really don't care. Equations. We can have Euler's method and other methods. They apply directly. All right, that's all for today.